First of all, I would like to thank you very, very much for giving me the opportunity to present you our work. My name is Eleanna Pirgianaki. I am a postgraduate student at the University of Crete, and I'm working at the IESL-FORTH within the framework of the European Horizon program called iPhotoCode. So today's presentation is entitled Non-invasive photoacoustic imaging for in-depth cultural heritage diagnostics. So I think it would be better to begin with some theoretical background so as to be easier for us to fully understand the following results. So the photoacoustic effect, in fact, is the generation of acoustic waves following the absorption of pulsed optical radiation by material medium, which is the absorber. Let me, do you see the laser pointer? Can you hear me?
Yes.
Okay, great. So this is the absorber. Now, the resulting pressure signals are then recorded in the time domain by ultrasound transducers. So this is the equation of the initial pressure, where, as you can see, it depends on Grunheisen parameter, the absorption coefficient of the medium, and the fluence of the laser. Now, according to the theory, the sensitivity of the photoacoustic effect is expected to be significantly higher than the one of the pure optical techniques. Moreover, since acoustic scattering is much weaker than light scattering, as it propagates through a medium, the photoacoustic signals compared to NIR or visible ones present up to 3 orders of magnitude improved transmission through turbid media. Well, of course, we know that there are many other techniques that are already used in cultural heritage science with actually very, very good results. So what is the added value of the photoacoustic technique? First of all, the system is portable and suitable for in situ measurements in galleries and museums. Secondly, the photoacoustic system is easy to assemble and operate even for non-experts. Thirdly, the photoacoustic system enables deep probing in optically diffusive media thanks to ultrasonic wave transmissivity. The photoacoustic techniques offers much higher optical absorption sensitivity than conventional optical spectroscopy. And last but not least, the photoacoustic technique can detect ultrasonic signals with transducers placed several centimeters away from the probed area. Now, the main goal of the research and today's presentation is to investigate and present the applications of the photoacoustic effect towards the in-depth diagnostics of cultural heritage objects. So in order to do that, we have performed measurements on 4 big categories of cultural heritage items, which are paintings and frescoes, metals and alloys, papers, and inks. As a first step, we aim to reveal hidden underdrawings in paintings and frescoes with a non-invasive way. Moreover, we have performed measurements regarding the assessment of degradation phenomena happening due to aging on paintings, papers, metals, and inks. We also tried to identify the different type of papers production. I mean whether they are made out of industrial way or non-industrial way, different types of paintings and pigments, different types of historical inks and metals, moreover, we want to perform measurements regarding the detections of regions where there is a varnish or unvarnished, uncoated regions on the surface of many cultural heritage objects. So this is how our photoacoustic experimental setup looks like. So we have a pulsed laser emitting at both 1064 and 532 nanometers. We have also a motorized filter wheel equipped with 2 different colored glass filters in order to select the desired wavelength. It follows a broadband dielectric mirror in order to direct the selected beam at the surface of the mockup, which is placed and secure on the top of 2 motorized stages in order to be raster scanned. And then the produced photoacoustic signals reach the surface of an air-coupled spherical focused ultrasonic transducer, and they are being amplified and digitalized by an oscilloscope, and the whole setup is controlled with a laptop. Now, we want to characterize our setup. So in order to do that, we drew a graphite dot, a spot, with a diameter of approximately 180 centimeters. Micrometers, sorry. And we irradiate it with 1064 nanometers laser. And this is how a typical photoacoustic signal looks like. You can see that we have negative peaks and a positive peak. Now, in the following slides, you will see extensively the term peak to peak. This is actually the distance between the negative and the positive peak of the photoacoustic signal. Now we have performed fast Fourier transformation on this waveform to generate a normalized photoacoustic amplitude spectrum representing the detection sensitivity of our transducer, which is approximately 1 megahertz. Then we image this dot with the photoacoustic system, and we extracted the pixel intensity profile, and the data points were fitted with a Gaussian curve, as you can see, and the full width at half maximum is approximately at 800 micrometers, which is also the lateral resolution of the transducer. Now we're moving on to our first big category of results, which are the imaging of hidden underdrawings. So before I show you the results, I would like to describe you what we have done. So we created some series of mock-ups made of a canvas or gypsum substrate. Then we sketched some underdrawings using a graphite pencil and covered them with different types of acrylic paints. Here I will show you only some of them. Then some of these mock-ups were coated with acrylic varnish, some of them were uncoated, and some of them were coated with a gel that I will explain you the reason afterwards. So we used both of photoacoustic system in order to image the underdrawings and NIR imaging, because NIR is traditionally used for this cause, and we wanted to check the effectiveness of the photoacoustic proposed technique. So here we have the first category of the results, which are the uncoated ones. And as you can see here, we have one of the challenges of the photoacoustic techniques. The photoacoustic system cannot give imaging of the underdrawings, and this happens because the parasitic signals from the surface of the mockup is stronger than the weakened ones from the underdrawing. So they reach first the surface of the ultrasound transducer, and the imaging of the underdrawing is not possible. But this is not the case for the NIR imaging, where, as you can see, we can have a picture of the underdrawing. But when we have a protected varnish layer on a mockup, photoacoustic technique can not only give an imaging of the underdrawing, but with a very, very good imaging contrast compared to what NIR can give. Now, whenever we don't have this varnish layer, we have created a gelatin gel that can easily be applied with a syringe and removed by hand. And we also tested that it does not cause any harm on the surface of the mockups. As you can see here at figure M, there is a zoom in region of this mockup without the layer, and on figure N, this is the same zoom in region after removal of the gel, and you can see that there are no visible alterations. Moreover, the imaging contrast is still very, very good and much better than the one NIR can give. So the pulsed energy for this measurement was 2.6 millijoules. The scanning regions are approximately 3 centimeters square. The scanning time is almost 90 minutes, and we irradiate did these mockups with 1064 nanometers wavelength because we know that in that region of the spectrum, both carbon and graphite absorb strongly, and carbon and graphite used traditionally to create underdrawings. Now, we focus again on the imaging of the underdrawings, but this time we want to compare the imaging contrast of those two techniques, photoacoustic and NIR. So in order to do that, we have prepared another series of mockups with gypsum substrate, in which we drew a similar, as you can see, underdrawing, and then we covered them by applying an accelerated paint layer thickness from 60 micrometers to 240 micrometers. And then we added a gelatin gel layer on top of them in order to be able to image the other drawings with the photoacoustic technique. So, as you can see, the photoacoustic image can give a far better imaging contrast compared to what an IR can give, even for the most difficult situation of the highest thickness of 240 micrometers layer. So now we want to quantify the previous observations. So at first, what we did was to calculate the signal-to-noise ratio for each samples by taking the average of the mean pixel intensity for the 4 regions located on the X and 4 regions on the background. As you can see, the SNR decreases exponentially as the thickness of the paint layer increases. Also, we wanted to compare the imaging contrast of those two techniques. For that cause, we used Michelson contrast value, where this is the formula, where intensity signal and intensity background corresponds to the average pixel intensity value for the X, the drawing, and the background. So, as we can see, even when the paint layer is very, very thick, the photoacoustic technique provides 3 times better imaging contrast than NIR. This can be explained because photoacoustic imaging works well in scattering paints, since photoacoustic waves present less attenuation as they travel through paint than NIR does, which has to pass through the paint twice. Now we're moving on to the same actual category, pigments and paints, but this time we wanted to check if photoacoustic technique can detect degradation on the surface of the pigments related to aging phenomena. Now, so what we did was creating another series of mockups with ochre yellow, and we used egg yolk as a binding medium, and we artificially aged them for 2 hours, 4 hours, and 6 hours, thermally aged them, and we also kept one sample as one mockup as a reference. We irradiated every sample at 10 spot. We took 10 spot measurements at the surface of each sample using only 1064 nanometers irradiation wavelength, and we calculated the mean peak-to-peak amplitude. So in figure E, you can see one waveform from each sample clearly showing an increasement in peak-to-peak photoacoustic amplitude as the aging time progresses. But if we look at the figure F, we can observe that from 4 hours and afterwards, there is a tendency to saturate, which is actually in a great agreement with the literature, where we can see that ochre yellow is a very stable pigment. But all these depend on pigment concentration. So we need to find an objective pigment degradation measurement unaffected by the pigment concentration. So we established a protocol. We used black tape as a phantom, and we put it on a microscope glass slide. We use this as a phantom because it is optically homogeneous medium and commercially available. And what we did was that we adjusted the pulse energies of the two wavelengths so that the peak-to-peak photoacoustic amplitudes results in a signal ratio almost 1. As you can see here, we have one waveform for the 532 nanometers laser, the green one, and the red one for the 1064 nanometers. These two have almost similar peak-to-peak amplitudes. This is what we wanted to succeed. Then we radiated the phantom at 10 different points with both wavelengths at each point and calculated the mean peak-to-peak photoacoustic ratio and the mean ratio out of these 10 ratios, which is almost to 1. Now we wanted to test the system, so we created another series of mock-up, again with ochre yellow as a pigment and egg yolk as a binding medium. But now we performed photo aging on them for a time period that it is equivalent to 10 and 25 years of natural aging. And now the main difference was that each sample have two regions, one coated with dammer varnish and one uncoated. So again, we took 10-point measurements in each region of each sample, and we calculated the mean photoacoustic amplitude and the ratio of 532 nanometers to 1064 nanometers. So the first graph is for the uncoated region. So as you can see, especially after 25 years of aging, the signals increasing at both wavelengths, but more strongly in the visible range, which is 532 nanometers, perhaps showing a degradation in the pigment. Now this is a graph for the coated region, where, as you can see, as time progresses, the 532 nanometers does not appear any change in the signals. Perhaps highlights the protected role of the varnish. But this is not the case for the 1064 nanometers, where we see that the signals are increased, perhaps showing a degradation in the varnish, the so-called yellowish of the varnish. This is also what we see if we look at the photoacoustic amplitude ratio graph, because in the uncoated region, the ratios are increased, because we have an increase in 532 nanometers absorption, and for the coated region, we have the different observations. The ratios are decreased. Now, we wanted to take the research one step forward, so we measured the same samples with nonlinear optical microscopy, because this technique can determine the depth to which the degradation of the varnish has progressed as a function of artificial aging time. And as you can see from the graph, as the aging time progresses, the varnish has produced a progressively stronger fluorescence signal. And again, the largest difference is at 25 years. Here is the green graph. So the results of these two methods are in agreement. So we're moving on to the second big category of cultural heritage items that we have performed measurements on, which are inks. And historical inks. So identifying the inks used in historical documents is essential because it helps us design the right restoration strategy and gives us important clues about their authenticity, origin, and of course dating. So for this purpose, we have used, as you can see, three types of inks: Chinese inks, sepia inks, and metal-legal inks. All these three were used in 19th century in Greece. And for each ink, we have used three different types of pens and writing methods, and we have taken the photoacoustic imaging for using both 532 nanometers wavelength and 1064 nanometers wavelength for each ink, and then we extracted the photoacoustic ratio image at the third column of each ink, as you can see. We did that because how we did that? We tried to find an automated and objective identification of ink degradation versus background for the accurate quantification of the photoacoustic signal ratios. So we used k-means, which is a machine learning algorithm which selects the regions of the image with stroke signals and using them to extract the ratio images. So here we have the mean photoacoustic amplitude ratio graph and our inks, the three inks we have used. And as you can see, regardless of the writing method, ink concentration, and pen type, the photoacoustic technique can differentiate between various types of inks. Here, for example, we have the Chinese inks that appears a ratio almost to 0.89, the sepia inks which appears a ratio almost 0.59, and iron gal in with a ratio of 1.7. That means that regardless of the different pen types, the photoacoustic technique can distinguish the type of ink by extracting a characteristic ratio for each one of these three. Now we have research progress again using inks. What we did, we performed measurements on some typographic inks. We separated these samples with the second industrial revolution period. So we have one document from 1859, which located chronologically before the second industrial revolution, and two other documents, one of 1888 and one at 1943, which belongs to the post-second industrial revolution period. So once again, we randomly select three regions from each document. We irradiate them. We image the typographic inks again using both 532 nanometers and 1064 nanometers wavelength, and then we applied again k-means clustering in order to obtain the corresponding ratio images. So here we have the photoacoustic ratio graphs, and as you can see, the two documents dating after the second industrial revolution exhibit signal ratios almost 1 and very, very close to 1. But the older documents before the second industrial revolution differ significantly and appears a ratio almost close to 0.7. So that probably means that the photoacoustic techniques may appear able to distinguish inks by production period. Now we're moving on to another big categories of cultural heritage objects, which are metals and alloys. Here we have three different alloys, as you can see, and each of them has a clean region and one or two with accelerated corrosion states. And as you can see, by calculating the photoacoustic amplitude ratio at 532 to 1064 nanometers, we can differentiate the corrosion states. Now, if we want to perform photoacoustic imaging on metals, we can distinguish the regions that are corroded with the clean ones, because the photoacoustic signal amplitudes are different, as you can see. And moreover, if there is a varnish layer, for example, there at silver 925, all the left region are covered with Ingralac varnish, and the right region is uncoated. So you can see that the photoacoustic signals are very, very attenuated when they meet a covered region, a coated region. So we can distinguish those two regions almost with negative contrast. Now again in metals, we have carried out some preliminary measurements on silver 99999. They are all polished, those coupons, but they are coated with five different kinds of varnishes: paralloid, wax, Frigilen, Ingralac with matting agent, and Ingralac without matting agent. And we also kept again as a reference without any kind of varnish. Also, these all coupons are not aged, but we plan to artificially age them in the near future. So, as you can see from the photoacoustic amplitude ratio graph, the reference sample gives a ratio one that is 1.49, and a similar ratio is obtained for the samples coated with paralloid and Frigilen and Ingralang without mating agent. And this means that all these varnishes, at least before aging, are transparent at both wavelengths that we use, 532 and 1064 nanometers, and the technique can still detect the metallic substrate. But this is not the case for the wax and the Ingralac with mating agent varnish, which appear to be not transparent, especially to 532 nanometers laser, and we can no longer obtain signal from the metallic substrate. Now, the final big category of cultural heritage objects are the papers. So we wanted to see if the photoacoustic technique can detect alterations and degradations on the surface of papers after artificially age them. So what we did, we used craft wrapping paper from mechanical semi-chemical wood pulp out of industrial production, and we artificially aged them under stable conditions of 80 temperatures Celsius and 78% relative humidity for 7, 14, and 28 days, and we again kept one as a reference. You can see from the graphs that as the aging time progresses, the ratio of the photoacoustic signal decreases. That perhaps means that the photoacoustic technique can detect early stage aging phenomena on papers. So, to conclude, the photoacoustic technique exhibits sufficient sensitivity for the early detection of degradations and alterations in various cultural heritage objects. The technique can detect the presence or absence of varnish with a spatial resolution better than 800 micrometers. There is also strong evidence that the photoacoustic technique can differentiate between various types of metals, alloys, papers, inks, and pigments. Moreover, the photoacoustic technique exhibits sensitivity to orders of magnitude higher compared to standard absorbance measurements. And the photoacoustic imaging contrast of painted over sketches has been at least 2 times higher than the respective contrast provided by, let's say, NIR images. And our future plans. Firstly, we want to focus the research on specific objects aimed at evaluating and validating the sensitivity of the technique for detecting aging-related phenomena. We want to perform analysis measurements on paper samples with fungal presence. Moreover, we plan measurements on aged things in order to attempt an assessment of the alterations they may exhibit. Moreover, we plan to organize photoacoustic measurements on objects with NIELO technique, metallic objects with NIELO technique, and higher corrosion levels. And the big picture is that we aimed to develop the portable photoacoustic spectroscopy prototype for in situ measurements in museums, galleries, and archaeological sites. I would really want to thank the iPhoto Called Horizon Europe project for the funding, our collaborators, and my team at Forth, Professor Fotakis, Dr. Chervalakis, Dr. Philippidis, Dr. Marie, and Mrs. Kristalia Melasanaki. Thank you very, very much for your attention, and if you have any questions, I will be happy to try to answer them.